Okay, I want to show you just a little more of what we're talking about with displacing the particles on a wave. Here what we're going to have is we're going to have a transverse wave. What that means is the energy is going to move in this direction, okay, essentially up the screen or forward. It'll reflect and it'll come back, but the particles, the string itself actually moves up and down this way, or left to right on the screen, so to speak. Okay, so in the demonstration I did in the classroom with the cord, I was displacing down. The wave would move down the string to the wall and that would reflect back on the top. So if you notice, the same thing will happen here. So I'm just going to displace this in this direction, and my wave travels down on one side and then it reflects and comes back on the other side. The speed of the wave moving forward as it moves is based on two things. Number one, the thickness of the material, or what we call the mass to length ratio. And they're using the term density here, which is really kind of incorrect. But we'll talk about mass to length ratio later. The second thing is by the tension. And any of you who play any kind of stringed instrument know that if you tighten the string, it's going to vibrate faster. It's going to have a higher pitch. And that's because the wave in the string moves faster up and down. I think I can adjust that and notice it's going to pick up speed in this case. Let me move that back down. Okay. Now, one thing I do want to show you is when we look at stringed instruments, they vibrate. Basically, they're fixed at this end and fixed at this end. And they simply, in the middle, it seems like they bounce back and forth, back and forth, back and forth. In the center, about here, they're going to only move about this much because they're really, it's a little tighter or it's closer to the end. Here, they might move a tiny bit, and at the ends, they're not going to move at all because they're fixed. Same thing, a lot of motion in the middle, a little bit of motion here, tiny bit of displacement here, and almost none up and down, or left and right, I guess, in the screen here. Okay, but when that's happening, what is really going on is it's still really a wave that's moving this way and a wave that's moving this way. And we've got, because we have these fixed positions at the ends, we call those things nodes, and where it moves back and forth the most we call the antinode. So I'm going to try and do that here as well. And to do it, what I'm going to have to do is try and basically displace this thing out. And when the wave gets to the end of the string here, I have to have this particle returned. So we'll see how well this turns out. And notice it's basically vibrating back and forth. You can kind of see a little forward and backwards motion because I can't do it perfectly. We can try one more time. But it looks like it's just vibrating back and forth. This is how a guitar string or a piano string would vibrate: left, right, or up, down, up, down. And it gives you a picture of like the very first one that I did with the cord in the classroom that basically looked like you're just moving a jump rope up and down. Okay, because you couldn't see the forward backwards motion in the classroom example, it looks like you're just doing jump rope. If I was holding one end and you were holding the other and somebody was jumping in the middle. Okay, now with our stringed instruments, of course, the displacement's not very big. They vibrate. You know, you might have a string that's like a guitar string that might be 30 inches or 25 inches, something like that, and it vibrates, you know, maybe a quarter inch back and forth. It's a really tiny amount of displacement, and it's very fast. Okay, so this is a little exaggeration of that. But we call this a fundamental. So the fundamental is the first time that something's vibrating back and forth, and essentially it gives us one hump. So it's either called a fundamental or a first harmonic. So if we're talking about stringed instruments, or when you get to woodwind instruments and things, obviously with harmonics, it's different pitches. Let me try this now with a second harmonic. And so what the second harmonic is, what I'm basically going to do is try to send a wave down here on top. And let me show you it without it being a harmonic, but I'm going to send a wave down on top, and when it gets down there, I'm going to send another one and get them to interfere in the middle. I'm going to try that again. But so right when it gets to this end, as it moves this way, I'm going to send another wave down, and they should interfere with each other in the center. So here's the one up, second one. And now notice right in the middle, they kind of cross, and you basically have canceling. These particles are almost not moving off the string at times, or off the center line, the equilibrium line, at times as they go back. Now if I can time that so that the height happens, the maximum height happens when it's halfway there, what we should get is that second harmonic fundamental of, my cat just showed up, sorry about that. So let me move this up, back down, and up, and back down again, and notice we get basically, wow, I did a pretty good job on that one. Okay, this would be our second time that resonance is occurring. Okay, so notice those particles in the middle are barely leaving the equilibrium line. Okay, and I did this on the string in the classroom as well, but we would refer to this as our second harmonic. Okay, And essentially what we have here is the two humps. So we have an antinode here, that's the hump 1, an antinode here, which is hump 2, and then 3 nodes. Of course, 2 at the fixed ends like we did before, but a node in the center where those particles are basically staying on the equilibrium line. Now, if I could do it perfectly, they would stay on the equilibrium line there. This is going to be important when we start talking about sound waves. Now, a stringed instrument does not vibrate this way. It always vibrates at just a fundamental. Okay, but notice what we have here is we have a full wavelength. So if I could pause this, which I can't, what we would see is basically we have a full wavelength. Remember, the full wavelength goes from fixed position up, down, and then back to the fixed position again. Okay, so if we could pause this, it would look like a sine wave where the wavelength is essentially from this dot here to this dot here. Previously, when we have the fundamental, and let's see if I can set that up again. Okay, notice this one, it's still moving up back and forth a little bit, but essentially it's vibrating back and forth. Let me try one more time. I can't get that perfectly. Anyway, that we have a half a wavelength if we were to freeze this. So we only have one hump, which is basically half a wavelength to start with. Okay, I'll try one more time to get that so we can see it. A little better. Okay, but the vibration just going back and forth, making just that one hump. Okay? And again, that's how our guitar or piano strings vibrate. And we refer to that as a fundamental. Notice we have exactly a half a wavelength. So if I have a guitar string and I say that it's 24 centimeters or it's 30 centimeters based on wherever I'm holding it against a fret. So let's say we have a 30 centimeter guitar string vibrating back and forth. The 30 centimeters would be exactly a half a wavelength. So the wavelength of that wave would then definitely be 60 centimeters in that case. We'll talk more about that later, but I wanted to see if I could get this to work and show it to you as a virtual simulation instead of the live one from before. So.